Magnetic braking is a type of braking which doesn't rely on mechanical pressure, as is common in most braking systems. We'll demonstrate this type of braking using a magnet and a copper tube. Unlike iron, copper is not a magnetic material, so the magnet won't physically stick to it. Therefore, a magnetic attraction cannot be the reason for any slowing in the fall of the magnet. A slit has been cut in the front of the copper tube so you can see the magnet as it drops. As you can see, the magnet falls much slower than you might expect. We can drop a non-magnetic metal through the tube and see how quickly it falls. It falls much faster. Therefore, magnetism must have a role to play in this process, even if the magnet is not being physically attracted to the copper tube. If we look down on the copper tube as the magnet falls through it, you can see that the magnet never touches the sides of the tube. Therefore, friction cannot have a role in the magnet's deceleration. Using the following cartoons, we can explain the processes that are actually happening. Again, we see the magnet dropping through the tube. The red lines are added to represent the magnetic field produced by the magnet. As the magnet falls, the magnetic field in the copper tube changes. This variation in the magnetic field induces an electric current, as predicted by Faraday's law. Faraday's law states that any change in the magnetic environment of the copper tube will cause a voltage to be induced in the tubing. This induced voltage creates electric currents in the copper called eddy currents. They're called eddy currents due to the circular motion they undergo. All electrical currents produce their own magnetic fields, which are illustrated in this diagram by green lines. Another law predicts the direction these induced electric currents and their magnetic fields will flow. This is called Lenz's law. Lenz's law states that when an electromagnetic field is generated by a change in magnetic flux, according to Faraday's law, the polarity of the induced electromagnetic field is such that it produces a current whose magnetic field opposes the change which produces it. Essentially, this means that the magnetic field created by the eddy currents oppose the magnetic field created by the falling magnet. It is the opposition of these two magnetic fields working against each other which slows the fall of the magnet. This video from the MIT Physics Lecture Demonstration Group demonstrates magnetic braking using a copper pendulum. The pendulum swings freely when the magnets are not switched on. Once the magnets are on, the pendulum experiences a changing magnetic field as it swings. This changing magnetic field induces a voltage in the pendulum, which creates eddy currents. The magnetic fields created by these eddy currents slow the pendulum to a stop. This perforated pendulum contains many gaps, and these gaps are occupied by air, which has a very high resistance to electrical currents. Weaker eddy currents means a weaker opposing magnetic field. This results in less magnetic braking or damping, and the perforated pendulum comes to a stop much more slowly than its solid equivalent.